Hi and welcome to Calculus 30 with Miss Verity. Today we're going to be looking at 3.3 strategies for evaluating limits. So to start off with, yesterday we talked about using the visual approach, so using a graph and looking off of the graph. But what happens when you don't have a graph? And you might not necessarily want to graph it yourself, especially as the graphs get progressively uglier and uglier. But when we're talking about direct substitution, so the limit as x approaches -3, we're just going to plug -3 in for our x. So -3 plus 9 all over -3 subtract 3. Well, perfect. That simplifies, and we're going to get 6 over -6, which is -1. So the limit as x approaches -3 would be -1. And our other one, so the limit as x approaches 2, well, 2 cubed subtract 3 times 2 squared. We're going to have 8 subtract 3 times 4 is going to be 12. Well, that's -4. So the log of 2x over sine pi of x over 18, the limit as x approaches 9. Well, as we start filling in values, we would have log base 2 of 9 over sine of pi times 9 over 18. Well, let's look and see what we can simplify. Well, 9 pi over 18 is really just pi over 2. So log base 2, 9 over the sine of pi over 2. Well, that's something we can evaluate. If we think pi over 2 is right there, and we've got the point 0, 1. Well, the sine is our y value, so that's over 1 technically. And I don't need to write the over 1. And log base 2 of 9 is just a number. That would be an exact value. So there's our solution. Our next one, as we approach 1, well, we'd have 1 squared minus 1 all over 1 plus 1. Well, 1 squared is 1, minus 1 is 0, over 1 plus 1, which is 2. That is just 0. So our next strategy would be through evaluating limits through sign analysis. Something you want to check would be, like your first thing you always want to check no matter what is if you can do it by direct substitution. Well, if we put 3 in, so 3 plus 3 over 3 minus 3 is going to give us 6 over 0. Well, we know that that doesn't exist. So in this case, we can't evaluate the limit by direct substitution. It wouldn't be like an exact value. Well, if we do our sign analysis, so all these questions have the same function, so we're going to go to 0 at -3 and 3. Our first one switches at -3, and our next one switches at 3. Well, we've got negative, positive, positive, negative, negative, positive. So overall, from -infinity to -3, we have a positive y values, then we've got negative y values, and then positive y values. We know that we have an asymptote at a certain value, but if we look at these, so we know that -3 is where our issue, our value at 3 is where our issue exists, because this is an asymptote. So our first one, we're approaching 3 from the positive side. Well, 3 from the positive side is this way. Well, as we're approaching it, we are coming from positive infinity. So this graph will be going off to positive infinity, so we would say does not exist, x approaches positive infinity. If we approach it from the negative side, so 3 from the negative side, we're actually headed off to negative infinity. Does not exist, x approaches negative infinity. Well, then if we look at the limit as x approaches 3, well, if we are approaching from both sides, notice we're approaching negative infinity and positive infinity. We have something that looks like, if we've got our asymptote here, we've got a graph that is doing something like that. And we learned yesterday that we know that that just does not exist. It's not approaching any infinity in general. It just does not exist. So determine the following limits. So again, same thing. These are all the same function. So we've got x, we've got x plus 1 and x plus 1. We could just treat it as an x plus 1 squared, but you know. So -1, and we've got also at 0. So switches there, So we have a sign change there, negative, negative, positive, negative, positive, positive, negative, positive, positive. So overall we are positive, negative, negative. So if we were to look at, I forgot to say, as we started, we would check, we'd plug negative 1 in, we'd have negative 1 plus 1 is 0, that's a 0 in the denominator, can't have it. First thing you check is always direct substitution. So negative 1, as we approach from the positive side, well, that's going off to negative infinity, so does not exist, x approaches negative infinity. If we've got, for b, negative 1 from the negative side, well, that's still going off to negative infinity. And then the limit as x approaches negative 1. Well, because as we approach from both the positive side and the negative side, we are approaching negative infinity on both sides. So that limit does actually exist because we're approaching the same infinity. So does not exist, x approaches negative infinity. Our next strategy we're going to look at is evaluating limits by factoring first. So again, really the first thing whenever we're looking at limits is you want to check, does the limit exist if you just plug the value in. So if I went 5 squared minus 6 times 5 plus 5 all over 5 minus 5, well, already right away we know we're going to end up with a 0 in our denominator. That's not going to work. Typically the next thing you would want to check would be this first step, which would be evaluating by factoring first. We want to see if we can cancel out any terms. And then sort of your next go-to would be what we just did, which was our sign analysis. So if I'm going to factor that, that's going to be multiplies to be 5, adds to be negative 6, x minus 5, x minus 1, all over x minus 5. Well, what do you know? We have terms that cancel out, and we're left with x minus 1. Well, we're going to take the limit now that we've canceled out a term as x approaches 5, because now we don't have anything in our denominator. Our denominator's not going to go to 0, and we can just say 5 subtract 1, which is 4. So the limit as x approaches 5 is 4. So our next one, our first step, if we plugged 1 in, 1 to the 5th is 5, subtract 1 is 0. We end up with an over 0, doesn't work. So factoring in our numerator, we have a common factor of 10r, and we're left with r subtract 1. And in our denominator, well, do you remember how we factored our difference of higher powers? So our r to the 5th minus 1. This is like difference of cubes. So this would be r minus 1 and r to the 4th plus r cubed plus r squared plus r plus 1. Our r minus 1's cancel out. And so now we're going to take the limit as r approaches 1. And we would have 10 times 1 over 1 to the 4th plus 1 cubed plus 1 squared plus 1 plus 1. When it's a positive 1, that's not going to make a huge difference. The biggest thing would be if we had negative 1s. Then our odd and even powers would make a big difference. So 10 over 1, 2, 3, 4, 5, 10 over 5, which is 2. So our limit as r approaches 1 is 2. Our next one. All right, so if you plug our numbers in, 6 squared minus 36, give us a 0 in the denominator. Can't have that. So to factor, multiplies to be 6, adds to be negative 7 is going to be x minus 6, x minus 1, over x squared minus 36. Well, that's a difference of squares. So x minus 6, x plus 6. So our minus 6's cancel out. And now we can take the limit. So 6 minus 1 over 6 plus 6, which is going to be 5 over 12. Can't reduce that anymore. That's our final answer. And then, so evaluating limits by simplifying first. So looking at this, if we plug 0 in, it's going to be in our denominator. We don't like that. So multiplying that out. You can multiply each term. It's cubed. We know what cubed means. But to try and speed things along, do you remember Pascal's triangle? Well, if it's a cubed, if we're in the third row, our pattern is 1, 3, 3, 1. And we know it's first term squared minus or plus, as you go up and down, you know, Pascal's triangle. You've done that. So negative 2 cubed is negative 8. We've got our negative 2 squared times 3, which would be 12h. And our negative 2 times our 3, which would give us negative 6h. Oh, sorry, this should be 12h squared. Nope. There we go. I am very wrong. 6h squared, because our h's are going up in power now. That's why. Plus, well, we would now have technically negative 2 to the power of 0, which is 1, and our h cubed. This would be, if we use our distributive property, plus 4 minus 2h plus 4 all over h. Whew. So if we combine our like terms, we've got h cubed, so that gets rid of that one, minus 6h squared, that gets rid of that one. 12h minus 2h is plus 10h. 4 plus 4 is 8, subtract 8 is 0. Excellent. All over h. Well, looking now, we've got a common factor of h, so we can divide every term by h. And we are left with h squared minus 6h plus 10. Well, now that we've got nothing in the denominator making it 0, we can take our limit as h approaches 0. 0 squared minus 6 times 0 plus 10. So that's going to give us 10. All right, there's our assignment. Pitter patter, let's get at her.